To understand energy, we first need to define work. Work is simply the application of a force to move an object. The way we calculate work is it is the product of the applied force and the parallel distance through which the force acts. The parallel part we'll address in one of the next slides, but for now, the important point of that is that's the product of force and distance. In other words, work is equal to force times distance. So if you want to know how much work it takes to move a book from the bottom shelf to the top shelf, then all you would do is take the force that you exert to move the book and multiply that by the distance from the bottom shelf to the top shelf. In this case, the force you have to apply has to be greater than or equal to the force of gravity. So the force you apply would be mg. That's just a side note right now. We'll apply that in just a minute. But the important point is that this force is whatever force is exerted. Now, when we write the numbers for work, then we need a unit to describe the work. The unit that we use for work, and also the same unit we use for energy, is the joule. Now, there's an important point to make here. That point is, what happens if the total distance the object moves is 0? Well, if that's the case, then following our equation, work equals force times distance. If the distance is 0, then no work is done. That means even if I have, say, an object right here, and I apply a force and move it around and bring it right back, I apply a force so it basically moves in a circle, I end up in the very same place I started. Distance is equal to 0, so my work is also equal to 0. Now, another very important point is that if the displacement is perpendicular to the applied force, then that means no work is done. So, for instance, if I have an object here and I push it to the right, so I exert a force to the right, but the object actually moves up, then my force is doing nothing. The object is not moving in the same direction as the force. Therefore, that is another situation where there is no work done, even though I am exerting a force. So let's do a quick calculation just to try this out. Let's say that you have an object that is 50 pounds, say a 50-pound sack of potatoes or something, and you want to lift it from the ground up to about chest height, about 5 feet up off the ground. Well, work we saw is just force times distance. So work is force times distance. So that's going to be 50 pounds times 5 feet. Well, 50 times 5 would be 250. The unit here in the English system is the foot-pound, or foot times pound. Now, we said the unit for work is the joule. That is if we use the metric system, in other words, if we use newtons and meters. So 50 pounds in newtons would be 223 newtons, and then 5 feet off the ground would be 1.52 meters. So that amount of work would be force times distance, 223 newtons times 1.52 meters, would give us a total of 338.96 joules. That is how much work is needed to lift that object off the ground and raise it to a height of 5 feet or 1.52 meters. Now, let's talk a little bit more about what happens if the force applied is parallel versus not parallel to the direction of motion. The maximum amount of work is exerted if the force is parallel to the distance. So, for example, we have an airplane here that's flying from the north to the south. wind is going from the north to the south in the same direction as the motion of the plane. Therefore, the wind, the force of the wind, can have the maximum effect in helping the plane move along. You have a nice tailwind to help push the plane along. However, if that wind is slightly off, say from the west, and the plane is moving from the north to the south, then the amount of work done is not maximum anymore, so the amount of work is reduced if the force exerts any angle at all to the distance of the direction of motion. Okay, so that covers work. Let's talk a little bit about power. Power is the rate at which work is done. Or in other words, it's the rate at which energy is transformed. So the way we calculate this, since power is a rate, that means it is the rate of work divided by time, work divided by time. And of course, recall, as we just discussed, that work is force times distance. So we measure power if we use the English system, feet, pounds, and seconds, then we use horsepowers. And that is the basic unit of power. 1 horsepower is defined to be 550 foot-pounds of work, or in other words, 550 pounds exerted over a distance of 1 foot per second. So 550 pounds times 1 foot divided by 1 second, that is the definition of 1 horsepower. Now in the metric system, we don't use feet or pounds. We use newtons and meters. In other words, work is in joules. So in that case, we have if we exert a force of 1 newton over the distance of 1 meter, sorry, this is a typo, that should say meters. 1 newton times 1 meter per 1 second, that is the definition of 1 watt. And yes, this is the exact same watt in, say, a 60-watt light bulb. So a 60-watt light bulb uses up 60 joules, or 60 newton times meters, worth of energy per second. That's what is meant by a 60-watt light bulb. So let's look at a quick example of power. So we're going to look at power exerted walking upstairs versus running up the stairs. So here's a man who is walking up the stairs, has a weight of 120 pounds. So he has to exert a force of 120 pounds to lift himself up the stairs. Now, if the force is 120 pounds and he has to climb up 10 feet worth of stairs, then that means that the amount of work he exerts is 120 pounds times 10 feet, or 1,200 foot-pounds. Now let's assume he takes his time to go up the stairs. It takes him 12 seconds to go up the stairs. If that's the case, then power is work divided by time. Work is 1,200 foot-pounds divided by 12 seconds. That means he is exerting 100 horsepower. Now, let's say that instead of just walking up the stairs, he decides to run up the stairs, and it only takes him 4 seconds to ascend. If that's the case, then the power is work divided by time, 1,200 foot-pounds divided by 4 seconds. In other words, he's exerting a power of 300 horsepower. He's doing the same amount of work, but he's just doing that work in less time. Now, when you use energy in your home, you end up getting a power bill. Really, you're not paying for power. You're not paying for the rate at which you use energy. You're paying for the energy itself, or the work done by that energy. So instead of using power, we know that power is work divided by time, or energy divided by time, since work is related to energy, which we'll discuss in the next video. We want to know how much energy that is. All we have to do is solve for energy, So that is power times time. So the power bill you get would be the power rate, the rate at which you use the energy, times the time at which you use the energy. That's really what you pay for in a power bill. We'll talk more about the power bill and do an example of that when we get to electricity.